Okay, yeah, so let's begin. All right, so this week's DSP 101 lecture is on pulse shaping. Um, I'm just going to minimize this out of my way. So, yeah, today we'll be talking about pulse shaping. Now, let's just remind ourselves where we are at in the course. So, first lecture, we covered sampling, Nyquist theorem, which a lot of you guys put to use in your first onboarding project, which is really cool to see. Um, which I'll talk about, actually, I kind of want to talk about that, but I'll talk about that at the end. And then we also talked about digital signals. We talked about sampling. We talked about modulation, analog modulation schemes. And then in lecture 2, we talked about digital communications. And I kind of just gave you guys like an introduction. So to just refresh ourselves, I talked about the two perspectives. There was the polar perspective and the rectangular perspective of looking at digital communications. And just keep in mind that the rectangular perspective is more useful from a hardware implementation standpoint, whereas the polar perspective is more useful from a theoretical perspective. I'm mentioning this because in this lecture today, I want you guys to think about the polar form in terms of like, remember the constellation diagram with those points on the complex plane. I want you guys to think about phase being the angle from the positive real axis and the distance from the origin in a straight line being the magnitude. Okay, so let's begin. So today we're talking about pulse shaping. Now, a lot of you probably haven't heard of this and have no idea what this means and where this fits in. So first, I'm going to start with what I usually like doing when I teach new stuff is the motivation. Like, why are we learning this? What's the need for me to introduce this concept? Because I was happy with the previous stuff. Why are we talking about this? So I want you guys to consider a scenario where you want to transmit a sequence of bits from point A to point B. It doesn't matter what the bit scheme is, just you have bits from A to B and you want to transmit them. So what did we learn last time? So we learned that with communications and digital communications specifically, what you do first is you'll pick a modulation scheme. So you could pick anything you'd like. Remember that the modulation scheme changes based on the channel conditions, how close you are to the Wi-Fi router. It depends on a lot of things, but the point is, if you're trying to transmit from A to B, you'll pick a scheme because it'll work. You define your bit mapping, as it's called. So if you look at this diagram here, I used 4 ASK as our example, and that just means that, remember, thinking about polar form, we've got 4 different magnitudes of our cosine wave, and they'll encode some sort of information. So this could be 0, 0, the first one. This could be 0, 1 as the second one, right? So that's how you'll encode your information based on the height of our cosine. Now, the question naturally, or not so naturally, but I'll force it to arise, is that how do you physically transition between these carrier states, as I call them? Like, how do you go from a cosine with amplitude 0 to a cosine of amplitude 1? Like, how do you, in time, in the time domain, do we just instantly transition from one amplitude to the other? Or if you're thinking about maybe QPSK, where we have, I'll draw it here, so you have the 4 dots, which basically that's saying you have the same magnitude, but your cosine wave is changing phase. Now, are we saying that we switch from phase 45 degrees to 135 degrees instantly? Or do we do it more gradually? And this is where the idea of pulse shaping comes in, and it's all about how you transition from one complex symbol to another. So this is the example I just showed you guys with 4 ASK, as it's called. So you have your cosine wave with 4 different heights. I don't know if I actually used 4 heights here. I got 1, 2. And here I've just got 2, honestly. So this would be like 2 ASK, 2 heights. So this would be 0, 1, 0, 1. You could also just do on, off, but this works too to convey the point. So one method, and I kind of hinted at this, for transitioning between carrier states or symbols is to instantly transition. So this is this idea of rectangular pulses. And that word feels a bit clunky now because it doesn't really fit in with how I'm wording things, but you'll see what I mean by when I say pulses. So what we're doing essentially with rectangular pulses is you send that symbol, so that amplitude for a certain duration called the symbol duration, and then at the barrier, you instantly swap to the new one. And then you instantly swap to the next one, and then boom, so on and so forth, right? Now, the reason why I'm calling this rectangular or square pulses, they're both words are used in these cases. Actually, quick pause. Okay, I'm recording just because I didn't record everything last time. Okay, we're good. I'm calling this rectangular or square pulses because you can picture like boxes almost. Like it's like this is the carrier state for this box, and the next box instantly changes, and there's no sort of gradual transition. It's just like boxes next to each other. That's why it's called rectangular pulses, because each one of these is like a pulse. So that's the first method of pulse shaping you'll learn about. And I have an animation here to show you guys, and I'm stuck on the marker. I can switch to the, what do I select? No. My God. Maybe I can switch to this. If I change slide right now, are you guys seeing the slides changing? Wait, like this?
Yeah.
Yes.
Okay, I just switched to my own tab, so I don't need to do the inline whatever. So if you guys have ever seen 3 blue, 1 brown, they do kind of these cool animations, and I kind of have been experimenting with like basically making them, vibe coding them basically. So this is a nice way to picture what we're doing with rectangular pulses. And it's a bit clunky, this animation. The other one's a lot better, but it gets the point across. So we have QPSK, let's consider that. You have your 4 points here. I'm going to pause. You have your 4 points spaced around the complex plane. And what we're doing is, let's say we go from the top right instantly to the top left. And I draw a line here, but really look at it in real time. So this becomes orange, and then the boom, boom, boom. You see how it's instant almost. Like, I know I'm showing a little bit of time to make the line, but you can think of it almost as instantly moving around this plane. Okay, instantaneous jumps between the symbols. That's what we have here. That's what you can picture with rectangular pulses on a complex plane. So what are the pros and cons of this? I've just taught you about one method. What are the pros and cons? So the first is bandwidth. Well, this is the big problem with square pulses. And I'm going to assume you guys haven't seen Fourier analysis yet, because some of you might and some of you might not. So I'm just going to assume no one's seen it. So Fourier's theorem tells you that any signal, and I'm on the left block here, any signal can be represented as a sum of sinusoids. The faster a signal transitions, the higher the frequency sinusoids required to build it. The keyword there is build it. So the idea here is, look, if you look at this bottom, you have a square wave, and you can actually create this using like an infinite sum. I'm giving a hint away here. Infinite sum of these sinusoids of increasing frequency. You start with the bottom one, and you do a quicker one, and so forth. So to build this instantaneous transition, you need to have a sinusoid with literally infinite frequency. That way it can transition instantly. So you need an infinite frequency component to make a square wave. Okay, so why am I mentioning this? Well, the reason is, if you think of square pulses again, if I go back to this diagram, you have these kind of square wave situations here. And at the boundary of one amplitude to the next, you're instantly transitioning to the new height or phase or whatever. And the point I'm trying to make here is that would require an infinite frequency component. And that's not good, because that means your bandwidth goes on for infinity. And you guys might not, the bandwidth is a whole thing I can make a whole lecture about. But the gist is you want to stick within your bandwidth that you're given for many reasons. One of them could be atmospheric, like physical reasons. Like, let's say the air conditions are only good from this frequency range to this frequency range. And if you go below it, like above it, like the clouds suddenly block your signal. That's one reason. Another one could be like governmental reasons, like you get a fine if you exceed the bandwidth you paid for. So you don't want to have infinite bandwidth. So we already know, and we could have guessed this, right? Like if you look at the constellation diagram animation that I made, you can see very instantaneous swaps, and that's just not feasible, realistic. Anyway, yeah. So this is what we have here. This is what I just said. So I'm going to skip this. So, what is a better approach? What's a smoother approach? Because this is not going to work. This is not going to cut it. Like, you can't transition between carrier states instantaneously. You're going to have infinite bandwidth. It's not going to work. So the obvious answer or solution here is just, hey, like, Tom, just transition gradually. Like, why do you have to swap from one amplitude to the next one instantly? Like, why do you have to have that jump? Why can't you just go from amplitude of 2 to amplitude of 1 smoothly, and kind of vary up and down? And that's the right answer. That's literally kind of the solution here. There's a lot more to pulse shaping than just gradual transitions, because there's another factor that I'll have to teach you guys about. But that's the main idea. Like, we don't want to do these instantaneous ones, so we do more gradual ones. So let me show you guys the animation for. This is one way of you doing gradual transitions. I call it using the sync pulse shape. But there's many ways. You could go in any random direction and transition, do loops, whatever. But I'm going to show you guys one right here. Right? So what we see here is that I'm hitting the symbol pattern that I want. It was the same as the previous one. So it's the top right symbol, then it's the left one, and we want to send the bottom left. But it's a smooth transition. And if you think about this as a polar form representation, so you've got a cosine here. This is what's representing, and the distance in the origin is the magnitude. So you've got a cosine. You're increasing the amplitude of it and then decreasing it, and increasing and decreasing it in that direction. And that's kind of. Actually, no. This is QPSK. So it's phase, not. It's all the same amplitude, magnitude at the 4 points. So you can think of it as phase is being changed. And actually, since it does go, a bit out of a perfect circle, sometimes it's going to be higher amplitude and then lower and stuff, right? But anyway, the point I'm trying to get across is you can see the smooth transitions. And the benefit of this is, well, lower bandwidth. Like, it's not instantaneous jump, so you don't need an infinite frequency component to make it up. So you have a lot smaller bandwidth, which is awesome. That solves that problem, right? Well, there's a second kind of problem. I'll get to that in a second. So let's just cover what this slide's saying. So it says that, okay, so it's saying that this is an important idea here. So bear with me. It's saying that, so we covered before that you send a sequence of symbols, and those symbols represent bits. And I've never really taught you guys or explained how the receiver itself actually decodes what symbol you're sending. It was kind of implied it knows what to do. But the true answer is, let's say you're doing square pulses. I'm going to take you guys back, all the way back to the front. So you're doing the square pulses here with the AFK. And I'm the receiver, and I'm looking at this wave pattern. Well, I'm going to have to decide what amplitude you're sending me in each slot. And the obvious kind of logical decision of when I should make my decision, timing-wise, is in the middle of the symbol duration of each slot. Like, that way if I'm making my decision on what amplitude you're sending me, at the very close to the boundary, if I'm a little bit off timing-wise, I'm going to miss it. So I should always kind of make my decision on what symbol you're sending me in the middle of the symbol slot. Okay? Hopefully that's somewhat kind of logical, right? So that's an important idea. So that's cool. So we make our symbol decision in the middle of the symbol interval. And this is called sampling, but it's a different kind of sampling than the one we saw before. Before, it was like you have an analog wave and you're sampling it. But this is like, when should I look? It's kind of that kind of sampling. Like, when should I read the symbol? So yeah, what we noticed then is that actually you don't need to hold the symbol value constant the entire interval, only when the receiver is looking, right? Like, let's say Juno is sending me that data, and I only need to, he only needs to make sure that the amplitude is the amplitude that he intends the exact moment that I'm looking, which is going to be in the middle of the symbol interval. So what I'm trying to say here is this explains why we can do this gradual transition, because as long as it equals that right amplitude at the right time, it doesn't matter what it is right after, right? And that's what this animation was showing. Like, it's not always a single amplitude, then the next one, we transition. And this is where synchronization becomes quite important. But anyway, hopefully that makes the idea a bit more clear. So now we have a requirement for what our pulse, our transitioning should look like. So we know that our gradual waveform, and it has to be gradual because we need limited bandwidth, must hit the exact correct symbol value at every sampling instant, regardless of what the neighboring ones are doing. But in between that, you can gradually transition. and move up and down slowly to decrease the bandwidth. So that's our goal. That's our one requirement. Now, there's a term for what I just explained, and the first idea is now I'm going to finally explain to you guys what I mean by pulse. Because I kind of hinted at it, but I've been explaining this idea of you got symbols and you want to transition between them. And I mentioned this idea of the symbol interval. And if you think about it, pulse is just the name we give for the shape of each interval. I'll repeat. So it's important. A pulse is the technical term that we've made up to describe the shape of each interval. So the interval could be a square, and then a square, and then a square. So we're using square pulses, or it could be a gradual, like a sine. Maybe it could be a sine pulses. But anyway, that's the idea of the term pulses. And there's this thing called a Nyquist pulse, and it's a very general family of pulses. It doesn't describe a single pulse shape. It fits many different pulse shapes. The defining part of a Nyquist pulse is that it is exactly 1 at its own center and 0 at other sampling instants. So what I'm saying is, if you look at this diagram on the right here, let's say you see these markers on the, I don't know if you can see my cursor, but I'll just talk you through the graph. So you can see the markers there on the x-axis. You got 0, 1, 2, 3, 4, whatever. So if you look at 0, you can see it's a height of 1. And then if you look at 1 on the time axis, so like let's say 1 second, it is 0. And then you look at 2 seconds and 0. These are all things called raised cosine pulses, so don't worry about that. Look at the black one. The black one is the sync. It's called a sync pulse. Anyway, these are all Nyquist pulses. I'm getting carried away. But look at 2, 0. Look at 3, they're all 0. Look at 4, they all equal 0. And this is the point. You want a pulse shape that is 1 at its correct instant and 0 at others. That way it doesn't interfere with the other symbol slots. And that way, at every sampling instant, basically every time I look at Juno's signal, I'm reading the correct value. Okay, I'm going to repeat what I just said because I said a lot. Now I'll repeat it differently. So remember, the key idea here is that we don't care about holding the symbol value, or the amplitude, let's say, constant for the entire symbol interval duration. All we care about is having it be the correct value at the right time. And that is what having or using a Nyquist pulse shape ensures. If you don't want to get into the 1 at sampling and 0 at other symbol sampling instance, don't worry about that stuff. Just remember that this is the term for the pulse shape that satisfies what I'm trying to tell you, where it's correct at the right time, and that's it, right? Okay. So another key term that you'll encounter probably in classes later on in your degree, or you'll see online, is this thing called the Nyquist zero ISI criterion. And I won't get too into ISI stuff now. I want to keep it on pulse shaping, but the idea here is that it's describing what I'm saying with this pulse shape, where it's 1 at its own sampling instant, but 0 at others, so it doesn't interfere. And the Nyquist pulse is a family of pulse shapes that satisfy the Nyquist zero ISI criterion. Okay. Anyway, that's a lot of theory. If you don't remember everything I just told you, that's fine. There'll be other key takeaways from this, and that's more about the gradual transitions and the bandwidth. That's the key idea here, and a bit more details in a second. So, right. Let's talk to you about this family of Nyquist pulses. So I mentioned there's a set of them, and the first one is something called the sync pulse. And it's this on the left here in the blue, that's a sync pulse. And that's what it looks like in the time domain. And on the right, that's what it looks like in the frequency domain. It's quite interesting, actually. So what we see in the frequency domain is that it has a well-defined finite bandwidth, which is awesome, because here it's in this imaginary graph. It's from negative 0.5 hertz to 0.5 hertz. And it doesn't have any larger frequencies. So it has a very well-defined, sharp bandwidth, and we like that. We don't want high frequency, and we want to stay in our bandwidth. So that's cool. We like that pulse. We already know it's a gradual one, so we knew it wouldn't have infinite frequency. We knew that already. Anyway, so this is the simplest Nyquist pulse. Yeah. So this last point, this represents the absolute theoretical minimum possible bandwidth required for zero ISI transmission, or basically having that idea of the correct symbol at the right time. What that means. So what's the catch here? There is a catch with the sync pulse, and it's actually we don't use sync pulses. We use other types of Nyquist pulses. Sync pulses we don't like, and actually it's impossible to use them. And the reason is actually quite simple: infinite time duration. So if I go back here, there's a rule in signals and systems, and it's called the time frequency duality. And it basically, in plain words, just says that whatever is infinite in one domain is finite in the other domain. So if you have finite time duration, which is what the square pulses were, like turns on at this point, turns on at this off at this point, turns on, off. It's very well defined and it's finite in time. It's going to have infinite bandwidth, infinite frequency. You see, finite, infinite. The same is true for this. This is basically the inverse of the square pulse. So you have in the time domain, you have this infinite time signal, but you have a finite bandwidth. But we can't represent infinite time signals in hardware. It's impossible. Like if you could tell, like that's basically saying, okay, we're going to turn on this pulse and it's going to exist for all of time and it's going to have existed for all of time. That's going to have been around since the dinosaurs. It's not possible. It doesn't make sense. So they're not truly possible. They're not physically realizable sync pulses. So you can't build a perfect one. Okay. Another reason is about this tail decaying. I'm not going to get into that, but that's another catch with it is that the tails, I guess I'll mention it. The tails, which are these like little side lobes, decay very slowly. So I mentioned the whole idea is that you want the tails to be like these side lobes to be 0 at the other sampling instance. And you can see they're actually quite big side lobes. If I was a little bit off, it's still a big error and I'm going to get a big mismatch. So we don't like this slow decaying nature. But the main point here is finite, infinite duration, in time. So bear with me, guys. We've got a few more things to cover. So that we've covered as a recap, square pulses. We don't like them. Infinite bandwidth. They're cool because in the time domain they're finite, but infinite bandwidth. Then I covered the inverse scenario, which was finite bandwidth but infinite time. We can't build that, so it's not possible. So we need to have sort of a mix of the two, and this is practical pulse shaping. So here's how I want you to think about this whole pulse shaping stuff. So you've got a family of pulses. You got pulses at the top, pulses just generally. Then you've got Nyquist pulses as a subset. And then within Nyquist pulses, you've got the sync pulse. And then there's a separate subset called raised cosine pulses. And each of those are defined by an alpha parameter. So it's a family of pulses that are all Nyquist pulses and defined by a parameter called alpha. Right? Okay, so they all satisfy the 0 ISI criterion, which is what all Nyquist pulses do. But they trade bandwidth and they have a bit larger bandwidth. But the benefit is that they actually don't exist for all of time, which is great. Which means that the bandwidth will have to slowly decay. But what you'll realize in communications, and I realize this through my classes in my master's program now, is that it's okay to have infinite bandwidth in a sense, as long as it decays is like a very small value. Because the way regulations work is that TELUS will be like, hey, well, like the government of Canada will be like, hey, TELUS, you can't have more than this magnitude of power outside the bandwidth we give you. But it's okay if the power level is below that. So you can have a bandwidth that kind of goes on and on and on, as long as it's very low power. But you can't do that with time. It doesn't really make sense. So anyway, the trade-off here is that we're going to allow a bandwidth that kind of goes on and on and on, essentially, for like a time domain pulse that kind of ends more abruptly. It decays slowly, but it doesn't exist for all time. And also we want a way to control the size of these side lobes. I mentioned that's an important factor. So this is what alpha gives us. So if you turn your attention to these diagrams, you can see they're indexed by different sizes. And one of the coolest connections I can make for you right away is that actually alpha of 0 is a sync pulse. So technically a sync pulse is a member of the raised cosine pulse family. And yeah, I just thought that was cool. So it's actually a member, but then you've got other ones. Like alpha 0.3, 0.5, 1. These are the only options. You can have alpha be anything from 0 to 1. 1 is the max, 0 is the minimum. And this is all the stuff I'm mentioning. You might be like, this is pretty theoretical. It's important for the next onboarding DSP project, because when you build the system, you'll have to define an alpha, an excess bandwidth. And it's called excess bandwidth or alpha. The same terms are used, but they both mean this parameter. So you'll see this come up again. So anyway, what are we doing here with the different alphas? Essentially controls our bandwidth and decay. So the trade-off is the smaller the bandwidth. How can I explain this? So the larger the alpha, the bigger the bandwidth. And that's why alpha is sometimes called the roll-off factor, or the excess bandwidth, right? So anyway, larger alpha, bigger bandwidth. But the benefit is you get faster decay. So they decay really quickly. And if you look on the left here in the time, alpha of 1 as the main pulse. And then you can see that side lobe gets like basically 0 instantly, which is great. We don't like the big swinging pulses. So, there's a bit of a trade-off here, as there always is in engineering. Okay, so here's the formula. Oh, what was that beep? Did you guys hear that?
I just had a quick question.
Oh yeah, what's up?
Okay, so I saw somewhere online where the roll-up factor, it also depends on, like, when you determine which roll-up factor you want to pick, it also depends on like the FPGA or like whatever chip is doing the signal processing, like, and its capabilities. So I think I've heard where if the roll-up factor is higher, it's a little bit more forgiving with like the time synchronization, I think. And then when the roll-off is lower, it's less forgiving, and then the FPGA chip needs to be more like capable. Is that right?
I mean, that sounds exactly right to me. If you look
Okay.
at, you said high roll-off factor means it can be a bit less forgiving. Like it's right. That's what you said, right?
Yeah.
Okay, so if you look at this diagram here,
more forgiving.
more forgiving. That's what I meant. So
Yeah.
with alpha equal 1, oh, when is this going to go away? Oh, it stays. Oh my god, it's disappearing ink. No, I need to turn on disappearing ink. Hold up. Let me show you this. So look at alpha of 1 here, which is this one. What we notice here is that the side lobe is very small. And the reason why we're saying more forgiving to timing stuff with FPGA is because I mentioned before, Juno, you're sending me data, and these are our sampling instance, and this is when I'm looking at stuff. This is, say, for 1 pulse, so I'm looking here and I'm reading whatever values associated with this pulse. But if I look here, I don't want the previous slot, which is what this is representing, to spill over and influence it. So it's going to be 0, and it's always 0 if you have perfect timing synchronization for these Nyquist pulses. But if I'm a little bit off, like me and you are a bit unsynchronized, and I'm reading these values you're sending me at slightly the wrong time, have a look at the diagram here. Compare this on the blue to this on the black. Do you see the difference in magnitude?
Yeah.
Yeah, so that's why it's more forgiving, because it's only a very small offset, whereas here you have a big influence, and it'll really add a lot to my wrong decision. Does that make sense?
Okay. So would this here, like, would the symbol sampling be like every, I guess, intervals of 2?
Yeah, well, here actually it's at intervals of 1. They only show every 2. But here it's,
okay.
it's 0, 0, 0. Yeah, it's zeros every sampling instance. It's of 1s. Yeah. So anyway, that's the idea. So there's a timing synchronization aspect to this stuff too, which is related to the decay.
Yeah. Okay, thanks.
Cool. Cool. So this is the formula for. So on the right here, you can see the different, like, I guess, frequency domain looks of the raised cosine pulse for different alphas, and there's actually a way to calculate this based on the alpha. It's this formula. I've used this in a class I've taken, so it's probably a bit more theoretical. I don't think you won't need to use this, I doubt, for the radio stuff, but it's good to know. So, like, for example, if you set alpha is 0, it's 1 over t, which is actually it's in like seconds, but 1 over t is actually like the sync pulse here. And then so alpha, just like if you increase it just increases the bandwidth, and this is a way you can like calculate that. Yeah. Just thought I'd mention that as a good formula to know. So I've got a few more animations here. So I've shown you animation of the square pulse. I've shown you animation of the sync pulse. Now let's see some of these raised cosine pulses. So first, I remember that I said that alpha of 0 raised cosine pulse is actually the sync. So let's look at the sync again, just for, comparison. That, cool. We know what that looks like. It's got quite a big overshoot, which is actually exactly what the other diagram was showing. The side lobes here are like these in between swings, here, which are very big. So if you're off, you could be all the way over here, right? Yeah. Now let's look at 0.25. Let's see how it changes with. Before I show you, remember what we're changing with the alpha. So we're increasing the bandwidth and decreasing the side lobes. So it's increasing the decay. So we should see smaller lobes, but let's see what we see. Okay. It's not too different. Honestly, it's not too different. I think with a different alpha, let's see what we get with 0.5 now. Looking pretty similar, I can't lie. See with the last one. Look at that. Okay, now we're seeing a shape. I honestly, this stuff is really new to me, so I wasn't sure what would see with the shape. But that is interesting. So it's looking more and more square-like as we go on. And if you think about it, that kind of makes sense. Like it's more sticking to the rigid. Like, I guess you compare it here. It's getting, yeah. Look at that difference. Let's go to 1 now. We kind of saw. No, did we see that? We haven't seen this one actually. Let's see. Cool. Really cool. That makes a box. So what have I just shown you? Now, if you think about, let's start with the bandwidth perspective. What I just showed you. I'm gonna keep this up here. So alpha controls the primary way you should think about it is alpha is called the excess bandwidth. So higher alpha means more bandwidth. So what we should see from this plot is higher frequency components somehow being baked in. So let's see if we can think about that intuitively. So for this transition, the start, let's just consider this one. If I was to go from the top right to the top left, the fastest way I can do that is a straight line, right? We've learned that the fastest way to go from point A to point B is a straight line. So over the same time duration, if I go there as fast as possible, that's the highest frequency, highest change, highest rate of change, which is what frequency kind of is, right? So this is showing exactly kind of what I wanted to show. So, and then if we would go to a lower one, let's go to I'll go back to, I want to go 0.25. Go back. Go through here. Here we go. 0.25. We should see it kind of takes a much more indirect path, which was what we saw. Like it's not going the quickest way possible because it doesn't have such high frequencies. Anyway, that's the bandwidth perspective of. I think these animations was cool to picture about the transitions. You could look at these for probably ages and figure out all kinds of things. Let me think if I can think of one more. So there was the bandwidth perspective, and then there was the side lobes one. So let me think about this. So as alpha increases, the side lobes get smaller. We kind of see that, right? Like look at the overshoot amount is huge for these side ones, for the small alpha. But then as you go to like alpha of 1, there's not much overshoot. It doesn't really go way beyond the value. So it's much more confined, much more less overshoot. So that's the idea. Yeah. Okay. So anyway, those are the different RC pulses, and you can see they all have different looks based on alpha. So that's a very key part. So the final thing I want to teach you guys about, which is the last thing you'll need, and it's very, very important. So lock in a little bit this last part, is this idea of the raised cosine pulse. So we just talked about the root raised cosine pulse. So we just talked about the raised cosine pulse, RC, and there's this last idea of the root raised cosine pulse. You just add root to the front. And basically all it's saying is it's more of like a practical concept in the sense that if we'd like to apply a raised cosine pulse in theory to a signal, like we're sending our symbol, Juno's sending me his symbols, and he'll want to use a raised cosine pulse to go between them to smooth out the transitions, to take care of things like time, the decay rate, the bandwidth, all these practical considerations. So he'll want to use those, a raised cosine pulse. But actually, turns out that using a root raised cosine pulse, the transmitter and the receiver is optimal. And here's why. So if you look at this math here on the right, you've got HRC in the top line. I'm going to switch to the little inline view. Here we go. HRC, which is the raised cosine. So this is what we want to apply. And if you can actually think about this as a decomposition of two kind of pulse shapes being multiplied together in the frequency domain, which is convolution in the time domain. If you don't know what that is, don't worry. It's just imagine you're decomposing it into these parts, right? So here you could call this part RRC and RRC. So essentially you have HRRC squared is equal to HRC. So then you could rearrange and go, okay, well, our root raised cosine pulse is the square root of our raised cosine pulse. And then actually, if I wanted to, remember the main goal here is just to apply the raised cosine pulse. I could do that by just applying two raised cosine pulse, root raised cosine pulses and multiplying them. It's the same effect, right? They're equal. There's equality. So that's what we do. But we actually apply this one at the transmitter and this one at the receiver. And then the net effect is a raised cosine pulse, but you kind of split them up and apply them at different places. And the reason is actually, I won't get into the technical reasons, but it's because of, where do I have it here? Maximize SNR. So, I just covered it. Whoops. Yeah, maximize SNR. So you can prove, if you're interested, I'd suggest you look it up. It's quite cool. But it's this idea of a matched filter. And that's what we're doing by applying something on the transmitter and receiver. It's matched, and somehow that maximizes SNR. But details aren't important for pulse shaping. All you need to know is that you do raised cosine pulses in two steps, one at the transmitter and one at the receiver. And I'm mentioning this because when you build your communication systems in GNU Radio, you will need to take account for the root raised cosine pulse at the transmitter. You'll build, then you have the channel, and then you'll have to configure the pulse shaping again at the receiver. And you might be like, why am I doing it twice? Well, it's because you're doing both parts of it that together form a single raised cosine pulse. Cool. So that's the last kind of main idea, and you'll literally directly use that in the project. So here's the big takeaway from what I've taught today, pulse shaping. So pulse shaping is the branch of communications concerned with answering one core question: what is the best way to transition between symbol values over time? It's the design of the actual time domain waveform used to carry a symbol sequence chosen to balance practical considerations like bandwidth, efficiency, SI, timing, all these things. It's a more practical picture of how we actually do communications. And that's all we have for pulse shaping.